G'day guys, today we're going to look at 10.4, which is all about network flow. A little bit different to our critical path analysis content. What we'll be doing here is looking at the flow of our network. So a good way to visualize these is to think about them as a bit of a pipe network and how much water can get through. And quite a lot of the questions will be in that sort of context. All right, so just some key definitions and information. Make sure this is all copied down. So we're going to use graphs to model flow problems. Now, all of these will begin at a source and finish at a sink. So like with our critical path analysis content, the edges are weighted, so they typically have direction and a value on them. The value is related to the flow capacity of the edge, so that's the amount of flow that can get through the edge. Each of our vertices will have an inflow, so the sum of the capacity of all edges leading into that vertex, as well as an outflow, which we'll be looking at a bit more on the next slide. But essentially, that's the minimum value attained when one compares the inflow to the sum of the capacities leaving the vertex. The maximum flow is also largely dependent on the capacity of the smallest pipe, and this will lead right into our maximum flow, minimum cut content we'll be looking at. All right, so just a few little things here. Just a quick diagram. This is what our network flows will typically look like. It's a bit different to critical path analysis, you'll notice. So in critical path analysis, our edges were labeled with values, sorry, not with values, but with letters. However, in network flow, you'll notice that the vertices or the nodes are the ones that are labeled with letters. So in that first one, A, B, C, D, E, and F, you can see there that the flow commences at vertex A, therefore that is our source, and it all converges and finishes at vertex F, so that is our sink. In the second diagram, what you'll notice is that B has a weighted edge of 100 coming into it. That therefore is our inflow. So that is what is running into vertex B. The outflow, you notice, is the edges that are leaving it. So think of B as maybe a town. It's got a pipe coming into it that has a capacity of 100 litres, or probably more realistically 100,000. And then it has the outflow, the three edges leaving it. So 30, 20, and 80. Now, a common misconception is to say that the outflow is the sum of those three edges, so 30, 20 plus 80, which is equal to 130, seen in the description here. However, you need to think about it in terms of how much flow is coming into it. If 100 is coming into it, it's physically impossible for the outflow to be greater than the inflow. It doesn't really make any sense. You can't have 100 litres coming into a vertex and then 130 litres just leaving it. Where did that 30 extra litres just magically appear from? Can't physically work. So for this one, the outflow from B is just 100, the same as the inflow, because that's all that can physically leave it if that's what's coming into it. With that third one, you can see that the inflow is the same. It's still 100. However, the three edges now leaving it have changed. So we have 30, 20, and 10. Because the outflow here is smaller, that means the outflow value is now the sum of these edges. It is 30 plus 20 plus 10, which is equal to 60. So if your outflow is smaller than your inflow, that will be just the value of the outflow. However, the maximum value that the outflow can be is the inflow coming into that vertex. Make sure as I'm going through, you're pausing it and taking any notes that you need to. Right, that brings us to probably the most important definition or most important statement that you're going to hear in this part of the topic, that the max flow is equal to the min cut, or maximum flow equals minimum cut. So it's a bit of a method that we're going to use in a couple of examples in this presentation. But basically, as the statement suggests, cuts are imaginary breaks in a network that divide it into parts and stop all flow from the source to the sink. We do need to watch the direction of the arrows. If it's not pointing towards the sink, then that capacity of that edge is ignored. So what we do is basically a trial and error process. We look at different cuts and work out the capacity of each cut. And then whichever the smallest cut is in our whole network, that's the maximum flow of our graph. But like with most things in this topic, I think this is best done with a couple of examples. All right, so here we have a table. We're going to create a network diagram and we're going to determine if the original flow is sufficient. So basically, if the flow that we're getting in is enough to meet the demands of these towns. So what we need to do is we need to first set up our network diagram. All of it is originating from the Rocky Bank Reservoir. So I'm going to draw that. You can either just draw it as a dot and label it R next to it, or you can put in a circle like this. So now the Rocky Bank Reservoir, that feeds the marginal dam. The quantity there, the flow is 1,000 litres per minute. Now from the marginal dam, we can see from the table up here that that's feeding the 3 towns, so Free Range, Waterlogged, and Dervishville. And that all 3 again lead into E here, that we can see from our table. So these all have directions, so I need to draw my arrows. All right, so now I need to put the quantities here. So from the marginal dam to Free Range, the quantity that we can see is 200. And because that's also the same to E, we'll put that on here. From the marginal dam to Waterlog is also 200. And lucky last, from marginal dam to Dervishville. So that's my first part. I've set up my network diagram. What I want to do is I want to work out the flow, or the maximum flow that I can possibly get from this network diagram. So what I'm going to do is I'm going to set up a couple of cuts. So basically all I'm going to do is I'm going to draw a line right through that stops all flow from source to sink, like such. So it's not possible for any of the flow to now get from the source to the sink. All of it has been cut off. What I do is I take the sum of those edges. So we've got 200 plus 200 plus 300 for a total of 700. So the flow of that cut is 700. I'm going to do the same on this side. See what I get. Also 700. And with this one, no matter how I shape my cuts, I'm going to get 700. Unless I put it at the very start here, it would be a little bit different. If I cut it off there, then it would be 1,000. Okay, so we've created our network diagram. We need to work out if the original flow is sufficient. So the original flow was 1,000 litres per minute. We can see that the demands of each town are 200, 200, and 300 for a total of 700. So yes, the original flow is definitely sufficient. It's providing 1,000 litres, the inflow per minute, whereas the outflow is only about 700. So the original flow is definitely sufficient there. All right, so what we're going to do on this slide is we are going to practice calculating the value of our network cuts to then calculate the value of our maximum flow. So essentially what we want to do is work out the smallest possible valued cut that we can get from this network diagram. Often when you're doing these, they will get a bit messy, especially if you're doing 6+ cuts like on this one. So you do need to be very, very careful when you are doing the calculations. So we'll start from cut 1 and go through to cut 6. So you can see cut 1 on the left-hand side. What you need to do is kind of trace along with it and visually identify every single edge that it goes through. So it goes through here and here. The value of those edges are 6 and 4 for a total of 10. So the capacity of that cut is 10. Often with SAC or exam questions, you will need to draw in your own cuts and work it out. So be careful that you are cutting off all flow from source to sink. With this second one, it goes through here, here, and here. So 3 edges it goes through. First one is 4, second one is 7, third one is 10. So for a total of 21. So that's quite high capacity. So at the moment, from my cuts, my max flow is 10 because that's my minimum cut that I've made. So minimum cut, smallest valued cut, is your maximum flow. So how much can get through it at once. All right, cut number 3 goes through here, here, and here. All right, so the value of this one, we've got 4, 11, and 10 for a grand total of 25, so quite a large cut. Cut 4 goes through here at 3. Now you notice it also goes through here at 11, but that's important what we're going to talk about in a minute. And it goes through here at 6. Now we do not count that 11. The reason for that is we've already cut off the network such that the flow cannot get to that edge. So because we cut that off at between A and B, it is not possible for the flow to get between C and D. So we don't actually count that in our network flow. So you've got to be really, really careful when you're making these cuts. Often the ones that are pointing away from the sink, they will not be included. Cut 3 was a bit of an exception there. But you need to be really, really mindful of that when you're making your cuts. Often when they're pointing away from the sink, they very frequently don't get included in the value of our cut. But you do need to just like visually have a look at the graph and think, yeah, okay, I've cut off from A to B, therefore it's impossible for the flow to actually get between C and D, so the value of that edge does not get counted. So cut 4 really only has a value of 9, the 6 and 3. Cut 5, so we got it down here where 3, value of 3. Here at the 7, again, I'm going to circle it, and up here at 6. So again, same thing. I've already cut off the flow between A and B, so it can't physically get between B and C, so I don't incorporate that into my cut. So this one has just gone through 6 and 3, like with cut 4. So that same value, oops, of 9. And lucky last cut 6, a bit more straightforward. Goes through 10 and 3. Therefore, the value of cut 6 is 13. When you're making your own cuts, just be really, really careful that you are cutting off the entire network. So if you drew cut number 7, like I'm just drawing right now over D, that is not a legal cut. Can't do that because it hasn't cut off all flow from source to sink. It's still possible for flow to get from A to E, could go from A to B to E. So cut number 7 is make sure that your cut's cutting off all flow for the networks. All right, that's pretty much it. Hope those videos helped. This is for exercise 10.4. Away you go.